In this video, we're going to look at tree diagrams. Now, a tree diagram is used to represent the probability of more than one event. Now, we've already looked at two-way tables. Now, you use a two-way table when we're trying to do something to the two values, like rolling two dice and adding the scores together. Tree diagram is used when we don't need to do two things. We do not need to do two things to the two events, but they can be separate. And in fact, a tree diagram can do more than two events. So let's look at our first question. So James goes to the arcade. He has one go at the teddy grabber and one go on the penny drop. The probability he wins the teddy grabber is 0.2. That means the probability he doesn't win is 0.8. Remember, we can do that 1 minus to get this. Probability he wins in the penny drop is 0.3. That means the probability he doesn't win is 0.7. Same thing, we can do 1 minus 0.3 to give 0.7. Now this is the structure of a tree diagram. So each set of branches gives us our event. So this first set of branches that I'm circling here is just to do with the teddy grabber. I've got nothing to do with the penny drop yet, it's just the teddy grabber. And there's two options when he plays with this teddy grabber. He can either win or he can lose. Now we've already worked out that if the probability that him winning is 0.2, the probability he'll lose must be 0.8, because guess what? These two branches must add up to 1. So that's the teddy grabber. Now we're going to look at the penny drop. So I'm going to change my color now. I'm going to take a different color and let's look at the penny drop. Now all of this is to do with the penny drop. Notice there's two sets of branches now. The reason we've got two sets is because the first set of branches is what happens when he wins at the teddy grabber. The second set of branches is what happens if he loses at the teddy grabber. So there's two possibilities. He's either going to win at the teddy grabber or he's going to lose. And if he wins, then we do a branch for the winning. And when he loses, we need a branch for the losing. Now the same thing applies. This is one set of branches, and this one set of branches must equal 1. So if the probability of him winning is 0.3, losing must be 0.7, because 0.3 plus 0.7 is 1 whole. Let's have a look at this one. Well, does it matter whether he won or lost the teddy grabber as to whether he'll win or lose at the penny drop? No, it doesn't. We call these independent. So that means that the winning probability at the penny drop is still 0.3 and losing is still 0.7. And that once again equals 1. So each set of branches equals 1. The second event always will have two branches if there were two branches in the first one. Now that's probably got you a little confused, so let's try another one. Okay, Natalie has 8 socks in a drawer. 5 of them are black, 3 of them are white. So let's quickly have a look. What is the probability that Natalie takes out a black sock? Well, how many were black? 5. Out of how many? 8. That means the opposite, the one of her not getting black, must be 3/8. But guess what? The opposite is white, and that is 3/8. This is a pair of exhaustive events. You either get black or you get white. I think Natalie has a very boring sock collection, personally. I have a lot more colours in my sock collection than black and white. Anyway, that's not the point. Natalie takes out a sock at random, writes down its colour and puts it back in the drawer. Later on, this little phrase here is going to be very, very important. Puts it back. Because if she doesn't put it back, then life changes. But as far as you're concerned, this year, all we're going to do is what happens if she puts it back. Then she takes out a second sock at random and writes down its colour. So what are my two events? Event number 1 is doing the first sock. Event number 2 is getting the second sock. And if she's lucky, they won't match. I love it when my socks don't match. I don't like wearing socks that match personally. So hey. Right, so let's have a look at what we draw. So in the first sock, what are our two options? Now if you remember rightly, last time we had win or lose. This time she could either get black or white. So on the end of the branches, I'm writing down what the possibilities are. On the branches, I'm writing down the probability. So what's the probability of getting a black sock? Well, we know that that is 5 out of 8. The probability she gets a white sock is 3 out of 8. There's my first event done. So my second event comes out. Look at this. I've also got 2 sets of branches here. Why? Because there was 1 set of branches here and each one of these options needs 2. So for the second sock, she still has a chance of black or white. If she got a black sock, if she got a white sock the first time, she's still got a chance of getting black or white. So let's have a look at the black. Well, she got black was 5/8. Well, black is still 5/8. Hasn't changed. Same sock draw, same socks. White would be 3/8. Black would be 5/8. And white would be 3/8. Let's just check. Is 5/8 plus 3/8 1? Yes, it is. 5/8 plus 3/8 1? Yes, they are. Are 5/8 plus 3/8 1? Yes, they are. Now this equals 1 doesn't have to be on the tree diagram. That's me just showing you what it's got to be. Right, third one then. What happens if we get no tree diagram at all and we've got to do it ourselves? So for a bias coin, the probability of getting a head is 3/5. Draw a tree diagram to reflect this. Now, here's the interesting question. Are we going to look at, I'm going to go for flipping one coin and show you what the diagram is going to look like. And then I'm going to show you what happens if we're flipping 2 coins. They should have told us, they didn't. So let's just look at one coin. If I flip one coin, we've got 2 possibilities. So I draw my 2 branches for my 2 possibilities. I either get heads or tails. Heads is 3 out of 5. Tails is 2 out of 5. Because remember, tails is the opposite. They're exhaustive, so I do 1 minus 3/5, which is 2/5. Let's have a look if we flip 2 coins. So my first coin would be my first set of branches. And up here, I'm going to write my first coin. Then for my second coin, I'm going to have another 2 branches. So all of these 4 here represent the second one. Now what could we have had? Heads or tails, heads or tails, heads or tails. So outcome goes at the end of the branch, probability goes on the branch, and we can label the events up here. So what's the probability of getting heads? Well, it was 3/5. Tails was 2/5. If I flip the same coin, this is not going to change. So it's still going to be 3/5 and 2/5 and 3/5 and 2/5. And there's my tree diagram. I never explained this word here, but let's have a quick chat. So biased means that it's not fair. So in a fair coin, it should be 50-50. You should have half of the time you should get heads and half of the time you should get tails. Biased means it's slightly weighted on one side. It's like a trick coin. Right, and that is how we deal with probability and a tree diagram.